We started to talk about this ensemble-based system, and we came to this. Can you close your laptop? Can you? Yeah, please, completely. Now we came to the point that we said that we have sometimes multi-classifier, and we have heard and we have seen a few of them. The challenge was that if we have these multi-classifiers, which decision do we have to pick? Because we can have one issue, multi-classifier, and they can give us different decisions. Some of them might be even the same. So we wanted to see how we can combine them. Actually, when we want to combine decisions, there are two ways of making this combination. One is we do that in the end at the decision part, so we have decisions, so we come to a point that we want to merge, or we can come to one single conclusion. Another one is when we want to fuse the data that we had at the beginning. Because if you remember, I said that we can use, let's say, one single classifier to do face recognition. We can do it in multi-color channels, in multi-domains, so we can have like different type of data. So we can maybe fuse data at the beginning. We will talk about that one as the last methods in here. And then we started to talk about two methods, right? If we go to the next slide at some point. Seriously. What did your thing do with my computer? Now we talked about majority voting, weighted majority voting, and majority voting was actually a very trivial solution in our hand, and it was something that we had in democracy. We just count how many says yes or how many says class A, and if it is the majority of them, we pick it up. And we said in the statistic, we refer to that one as mode because it's most frequent decisions that we have. And we said because we are talking about the classification, recognition, we are actually dealing with kind of probabilities, right? We have some tests, some of them are classified correctly, some of them are classified wrongly, so we can come with some probability value. As we can come with some probability value, when we are talking about each of these methods, we will talk about some probabilities. So I will show you some formulation, but we will go through some examples when we are talking about them. So we got the idea of the majority voting, right? We said that like in a class, everyone is equal, and I will show you one object and say that what is this? Some people will say that, let's say, a ball. Some people will say that an apple. And in order to make a decision, we see that what is the majority saying, and we pick that decision. Well, we said sometimes, due to either the nature of the classifier or the scenario that we have, we understand some of the classifiers are better or are stronger in that specific type of question. Do I need to tell you that put your mobile phone also in your pocket? I'm grown up, right? So what happens now is that some of these classifiers are more important. They can maybe discriminate better, but still it's probability. They may discriminate, but wrongly. So what happens is we assign them weight. We do not treat them equally. And I gave you this example. We can do the voting in the class, but there are a couple of the students that say I like them more. So if they say something, it will be more useful, or I will consider it like more biased towards that one. We understand making a biased decision in general in the life is not good. So the same thing is valid. But if this bias is towards something that we know it's better, it makes some sense. Let's say you do the face recognition in YUV, and you know that Y has a better, let's say, representation of the data. So if you use the classifier, we will give higher weight. But you should always come, if you want to write a paper, you have to come with a more scientific reason that why you assign these weights. Like heuristically, we find this weight is not something which is very useful, because someone at some point can come with a counterexample and destroy all the generality that you achieve. Now, apart from this weight, what else did we talk? I think we will talk further. So let's continue by reviewing the formulas. We said this is the majority voting that we have. It means that we look at the decisions, the one which has been developed or repeated most frequently, we will pick that one up. and the weighted one, we also multiply this decision by weight, and we accordingly find it out. We said multiplication by weight is that it means some of the decision you have to put like this classifier a couple of times. In other words, we are boosting that one higher, right? It's like that. We want to see whether we want to drink Coca-Cola or drink beer, and in order to make a decision, I will bring some of my friends who loves beer into the class and say, now let's do the voting. So I'm increasing the probability of making the voting of the beer. Of course, it doesn't make sense if I have, let's say, 3 classifiers and I assign a weight of 0.9 to one of them, because if you kill all the others, right? So we have the weight should be quite meaningful when we want to make it. We also talk about this one. What will happen if, let's say, we have a majority voting and the number of the votes are equal to each other, and assume that we have 5 classifiers and each of them says different classes. Which one do we pick? Yeah, I mean, based on how we are doing the discrimination, the one which has the minimum error, we will pick that one. And if there are like multi decisions and some of them like have 3 votes in here, 3 votes in there, then we look at the summation of these type of errors. Now, another methodology that we have is something which is called a mean rule. Let's see what the mean rule works. Now, in the mean rule, we mean an average, is this. We are calculating our discrimination factor, like the probability of making decisions, or like if you are using Euclidean distance, the Euclidean distances. Now, in order to come up with a decision, whether it is what is the total when you combine the decisions is, we are adding all these values that we have, and we get the average value and we make the decisions based on that one. So what I mean is this. Let's think that we have a phase recognition system which is using PCA, right? And we are doing it in, let's say, R, G, and B color channels, right? So we have 3 decisions, and we want to see which class I have to go. When we were in the grayscale, you did it in your homework too. What you were doing, you were using this ion phase to calculate the ion phases, then you look at the distances, and you were using some Euclidean distance, right? And let's call it V. And this is our Euclidean distance. Now, and when I have this value of the distance, what I would do, I would compare, I will calculate this one between my test and the training. And the one which is minimum, I say that this is that class. Right? This was the way that you were doing in your PCA homework, right? Right, Anton? So, now what I want to do is this. I am calculating dr, dg, and db between the test and the training I. So, because I have lots of trainings. So I calculate the test and the training of I, and the test and the I's training that I have, dri. Now, I know that if I look at only red, I can calculate the minimum value in here. If I look at here, I can calculate the minimum value in here and see that which class it says. Or if I do it in blue, I can see that what is the minimum distance, and I announce that one as my class. Or what I can do is this. For any specific I can add dr, dg, and db. So I get one new value. I call it capital D, which is the summation of these 3. So what happens, I have sets of these, isn't it? So I can look at what is the minimum value, and if it says that, okay, it corresponds to class 10, I declare that the class 10 is my class. So in the ideal case, what happens, if I belong to class I have the minimum in R, I also have the minimum in G, I have the minimum in B. So if I add all of them, I will be minimum in O. If we don't have, practically we don't have this situation, but if we don't have a very extreme value at any of these ones, the addition of these ones should not change the minimum. If, assume that this says class 5, this says class 5, and let's say this says class 4, because maybe it has the minimum, this says to class 4. If we look at the second minimum or the third minimum, we will see that actually B was also going to the class 5. Do you get the point? In other words, we don't have a very extreme job. Like it's supposed to be R and G says class 5, B says class 4, but if you look at the second, third, fourth, or fifth minimum value, we are not going towards 5.
What do you mean by the second minimum value?
You know that here we have lots of distances, right? So let's sort them. So we have the D minimum.
Okay.
Let's call it D minimum 1, the smallest value. Okay. Then we have D minimum 2, the second minimum value. And the third minimum value, and so on. And the last, what is the last minimum value? It's a maximum value, right? So now, if you see, we can add all of these values. If we do it, this is a method which is called the sum rule. Also, what you can do, you can add all of this one. How many decisions I have? 3. You can divide the result by number 3, and we get a mean or average of these distances. So I can look at the average of these distances. So this is what it says. So there are two methods which you can see that they are very correlated. Actually, they result into something exactly the same. One is we are only adding these ones and we get the result. Or we can also divide them by 3 and we look at the result. So mean rule and the sum rule ending into something same. Why? Because it's just scaling the value, linearly scaling everything. In other words, I look at the distances and I see that the distance are 100, 101, and 102. If I divide everything by 10, what will happen? I have 1, 1.1, 1.2, right? It doesn't change anything. It's just a scale the values. So this is called the mean rule. Now, indeed, we can do weighted mean rule, as we did for the weighted majority voting, because maybe we know that in one of the color channels, let's say, or for one of the specific classifiers, we have a better performance, so we can give a higher weight. Okay, we can give a higher weight. Like we are doing it in YUV, let's say that we give the weight 2, 1, 1 to each of these color channels. In other words, we are biasing towards the decision that we are making in Y. Now, there are two things that you have to consider. We are representing usually we are representing these methods by using probability. And while we are talking about the distance. Can you tell me that what is the relation between the probabilities and the distance that we are calculating? You know, we said that the best one is that we have a full match. What is in the full match? What is the distance? 0. So what is the relation between the probability and the distance from recognition point of view? They are reciprocal of each other, right? In the sense that if the distance is 0, what is the probability value? 1, right? So now what we have, this is something that you have to keep in your mind when you are reading some papers or you are using some formulation. So usually people, when they are using distances, we understand that they try to go down to 0. So maybe when you are assigning the weight, let's say sum rule, you will assign the one that you favor more, you assign the smaller number, right? Because you want to make it smaller. If you multiply the distance by 2, 0.1 multiplied by 2, it will become 0.2. So this is something that I assume that you understand how you have to do it. When we are dealing with probability, these weights are greater than 1 because we want to say that, oh, I want to increase the probability of the win. But when we are talking about the distances, the one that you favor, you give the lower these weight values, because if you give a higher weight value, you mean that, oh, I try to make this distance as big as it is possible. So I don't like this method or this specific channel. We are talking about some statistics like majority voting. Mode, we use it. In mean, we use it. And I said that if weighted mean, we can use it. Or if you don't divide it by a value, we can have a sum rule. What are the other statistic terms that we know? Minimum, maximum, median. And actually, we can use the minimum, maximum, and median in order to make some decision. Now, this minimum, maximum, and median are also very useful. Depends on the type of the data. Sometimes, let's say you are doing recognition in some different kind of channels, and one of the channels, all channels are very good, but one of the channels are acting very bad. Like here, it says class 5, the minimum distance is, let's say, 0.01. This one says class 5, the minimum distance is 0.01. And if it wants to say class 5, the minimum distance is 100. So you understand, if you use sum or mean, if you kick out of being class 5. So what happens, we can use, let's say, something like mean. If we are dealing with probability, we understand that we can easily use something like max. Or if you have much more decisions and you know you have sometimes some impulsive decisions, but you don't know which one it is, median is something which is very good. Why median is better if we have some impulsive decisions, some impulsive value? What is the difference between median and average?
Average is susceptible to extreme values.
Yes, average is very sensitive to impulsive values, to extreme values. Whereas median is not being changed if we have extreme values. So we can use median. Now, there is another method which is used if we have classifiers whose values, or let's say the probability of guessing correct is very high. So imagine you have 10 methods and 10 classifiers, and all of them, the probability of the winning is very close to 1. And we can, if this is the case, instead of adding the numbers, what we can do from probability point of view, we can multiply them. Right? We can multiply them, and it's called product rule. What is the weakness of the product rule? It's a very sensitive method, but what is it sensitive to?
Minimum value.
It's very sensitive to minimum value, which is, what is the minimum value? Probability 0, right? Probability 0. Because imagine I have 5 classifier and the probability of saying class 5 is 0.9, 1 even, let's say 0.9, 0.8, 0. What is the result? 0, because if you multiply it with 0, everything will go down. Or if you multiply with a very small number, it will go down very much. Now, this is the generalized product rule. So all these methods, which are kind of known methods, but it's very useful if you have multi-decision to use, are happening at the end. Let's say from programming point of view, you are writing your code, you are doing your decision making, you are using your SVM, you are using your PCA for H, S, I, or R, G, B, so lots of kind of channels and everything, and you make your decisions. So you have lots of decisions. This is class 1, class 2, class 1, class 3. So you want to know now, which decision do I have to pick? Right? So in that case, we can use those methods. But as I told you, sometimes before we come to these decisions, we can go back at the data level and do the combination in the data level. It is a method which is known as FVF, Feature Vector Fusion. And what we're doing here in FVF is this. Imagine you are using PCA in R, in G, and in B. We know that every face that we have is represented in the IM face, right? So I have one IM face in red, one IM face in green, one IM face in blue for the test and training. What I can do is this. I can take this IM face. then I can concatenate this one on the bottom of that one, and then concatenate this one on the bottom of that one. So what happens, I have one big INFX for training, and I can have the same thing for the test. Now, instead of having a small, three of the small ones, I have one big one, and I can calculate, let's say, the equivalent distance and make the decision. Now, it will help, it will boost the results because I have now everything in one go and I can make the decision. So if something caused some error, the other one is compensating. There is a small problem. It takes lots of processing time. Why? Because yes, inputs are bigger. Imagine that you have 10 type of features and you put them together, it will be huge. But it will give a very good result. So if we don't have much of processing power problem, then FBF is usually a very strong method. But the difference between FBF and the other methods that we have talked is this. FBF is happening at the data level. We are fusing it before we give it to our classifier. Is it possible to combine the data fusion with the decision fusion?
If you were to combine some of the data.
Let's make it yes/no question first. Is it possible to do it? And let's make the decision by using majority voting. Who says yes, it is possible? Raise your hand. Okay. 1, 2, 3, 4, 5, 6, 7, 8 people says yes. Who says it is not possible? You don't have any opinion? Who says it is not possible? Raise your hand that this is not possible to do it. Kadri, what's your feeling?
Sleepy.
No, feeling about being sleepy. Can we have data fusion and decision fusion at the same time? At the same time, I mean, in the same algorithm.
What do you mean by decision fusion?
Like majority voting, like some rules, you know, there I have decisions and I look at what is the majority of them.
I have different classifiers and then you fusion the decision. That doesn't
Thank you, Kadri.
No.
Yes. Now let's see what Kadri says. The other one.
Let's say no.
No, it's not possible. Fatima?
No.
It's not possible. Aygun?
I'm confused.
What is the source of confusion? Anton? Yes. Well, it is possible, but we understand that we are increasing this computational cost. In the sense that, imagine we have, like the example that we have here, R data, G data, B data. So we can fuse them and have huge data. And then I can apply, let's say, PCA. I can apply SVM. I can apply LDA. So I can have series of decisions. So at the end, I can also combine the decisions. Look, combining all of these ones with high probability will boost you. But the question is that, what is the amount of computational cost that you are introducing when you are doing this fusion, and how much is the amount of boost? If you are boosting by 1% and 2%, with high probability you would ignore it. But if you are boosting it by, let's say, 5%, 10%, I mean, it depends on your scenario. Maybe even 1% is significantly huge for your purpose and you want to do it, then you do it. If you go and look for boosting, you see that there exists lots of other algorithms, like ADA boost, which is very, very famous and very useful. But they are more complicated in order to implement it. But it will be now easy for you when you go through the description of that one, because you have now some fundamental knowledge about the other techniques, which are also being used there. Do you have any question about the fusion of features and data?
I didn't understand this minimizing thing.
Minimizing what?
Like calculating the big D and calculating the small d's.
No,
How
but
do you do that?
this is the equivalent distance. D is equivalent distance.
Between what?
In the sum rule, you have, let's say, for your test and training one, you have one equilibrium distance in R, one in G, one in B.
Okay.
You can add them and put the capital B.
Understood. Thanks.
Now, if you remember, there was a week that I was on here and Pejman came and we talked about some data partitioning methods, right? And we had something which is called k-fold cross-validation. What we do, we take some part of our data out, we keep the rest and we use it as a test. It's already labeled, but we treat that it's not labeled so we can see whether we have an error or not. And in order to make a very correct conclusion, we have to randomly pick these ones up. Because maybe it happened that this is a very biased set of tests. So we have to randomly try it and then we average that out. Or there exists another method which is called leave one out. And you keep one out, you use the rest for the test, but you try for every single element in order to come to a conclusion. So now based on this one, there are a few quiz questions. For each of the following statements, write true if it is mostly true, or false if it is mostly false, and then explain why you have this true or false decision. 1, in part A, cross-validation can reveal overfitting. Is it true or false? Overfitting is a danger when learning in classifier, but not when we are doing the unsupervised learning. In other words, overfitting is a problem in the classification. It is not a problem in the clustering. So think about it, because in the next slide I have the answer to both of them. Let's say 1 minute for each, 2 minutes, think about it, and then we will answer it together. See lots of scientific faces, that's very good. This was an exam question at some time. So Ozan, what do you think about the first one? Cross-validation can reveal overfitting.
I think it is true.
Why is it true?
I don't remember the cross validation, but the names looks it is true.
Okay. Eric, what do you think? Apart from the name looks like very good. It's true. If it is true, why it is true?
Because with cross validation we choose the testing data and training data randomly. So we don't have so much bias.
Maybe this can help you. You know, we have the word can, which means that there can be a situation, if this is true, there can be a situation which it will not result into overfitting.
Yeah.
But here it means that cross-validation have a potential of making the overfitting. So if you say this is true, you have to tell me under which condition it will result into an overfitting. If this is false, you have to give a statement that it can never result into overfitting. So when you say this is true, this is your answer, you have to say under which condition we will get overfitting in the cross-validation. And I think you can answer to this one if you remember how we can have overfitting. When did we have overfitting? When did we have overfitting in general?
When classifier classifies very well on the test set or training set.
Then we are very accurate, absolutely true, when we are very accurate in the cross-validation. In other words, we are going through every single dots in the data that we have, then we have overfitting. Why overfitting is a problem?
Because like if we have like a different
Look, we have this data, and overfitting means that you go over all of them. What is the problem with that one?
doesn't generalize.
Yes, we cannot generalize if we are overfitting. So this is the problem. This is the problem with overfitting. So this is true because if the cross-validation, if it is very accurate, it can cause an overfitting, which we cannot generalize. So we go to the next question. Overfitting is a danger when learning a classifier, but it's not a danger when we are doing an unsupervised learning. True or false? Ozan, don't tell me that it was true, so this should be false. Because I have a high potential of asking 6 true and false questions, and all the 6 are true. So
that means it should be true.
yeah, so all can be false. Don't make a pattern out of the.
Is that subject?
Yeah. Although don't make a pattern. Don't make a pattern. We already give you a pattern, so we just try to use your knowledge. So overfitting, quantum, is a danger when we do the classification, but we don't need to care about it when we are doing clustering. You think this is true?
But maybe we have a redundancy.
Where does the redundancy come from?
In unsupervised learning.
What do you mean redundancy? You mean that, oh, this data I don't like them, we are redundant, you throw them away?
No. Repeat the
Classification in cluster, we don't have a classification in cluster. There are two different things. Kali, what do you think? So you said this is true in general. We don't, your explanation was not correct, but I don't know even if your answer is correct or not. But what do you think?
True.
True? Why do you think it is true?
I'm not like 100% clear or sure of myself, but to me it seems like that when I learn a classifier, I can go very too precise about it. But
yeah, I mean, okay, let's look at it from this point of view. Overfitting is happening when we are very accurate, right? When we are making an equation or a pattern, it goes through all our data. Now, look at my sentence. I'm repeating it. Overfitting is like we're trying to find a pattern or an equation through our data. But
unsupervised learning, you don't have the
you know the question. We have the data, but
it's true, but
you don't need data.
no, we don't need the patterns in the cluster.
We do need the pattern. That's whole the idea. Even if it is labeled for the supervised. What is the definition of supervised learning? When you are training your system and you go to the training, you already know what are the labels. But at the end of the day, someone comes, you don't know anything, and you want to see which classes it goes, isn't it? So it's still, the whole idea is that you want to find a pattern. So you want to find a pattern. Oh, you wanted to say something?
Go
Oh, okay. So
on.
now,
I don't know, maybe I'm.
no. Let me repeat my sentence for the third time after that is overfitting means that we have a data and we try to find an equation or a pattern over the data, right? Now, did I say that it's a labeled data?
No.
Did I say that it is unlabeled data?
No.
So in other words, for data, I can go and find a very accurate pattern or equation over my data. In other words, this is false because overfitting is a threat for supervised and unsupervised learning. Because the nature of the overfitting means that I can be very accurate in what I have, what the data that I have, and I cannot generalize it later. So the answers were true and false, and I just discussed about the results. So next question. You are a reviewer of the journal paper. Okay, you are a reviewer of a conference paper in this case. And you are facing two papers, let's say of the same topic, or which have two statements. Now you have to make your mind whether you want to accept or reject these words. You can accept both of them, you can reject both of them, but you have to provide a reasoning. And the statements that have been written that you need to make your decision based on that is this. Paper A has written, my algorithm is better than yours. Look at the test error rate, reported result for the best value of, let's say, F. Person B has written that my algorithm is better than yours. Look at the test error rates, reported result, so both of them says that look at the error rates, reported result for the best value of L, chosen with tenfold cross-validation. So which one is the one that you want to choose to accept? Which one is the one that you want to choose to reject? Or if you want to accept both, why? If you want to reject both, why? Yes, Eric, you are a critical person and you need to make a decision whether we have to accept these papers or reject them, or accept one, reject one.
I would reject the first one.
You will reject the first one. Why?
Because I don't know how the results are, well, how the testing methodology is. What is the
Okay.
testing methodology?
What about the second one?
I would have checked the second one because it specifies how the results were.
Yeah, it's absolutely correct. The first one we, unfortunately, can accept or reject both, but it will be rejected in the sense that there are missing information. We have chosen L based on what? Which test data? What methods? But here we know that cross-validation is a very appropriate technique, a very appropriate methodology for selecting our parameter. Now, I have one slide, but I'm not so sure if I want to show it to you or not, because I don't want some of you run hating. And it is your last homework. The last homework is regarding to this majority voting, some rules, mean rules. I don't want you to run and say, oh no, we have the project that we have to prepare, an exam is coming, oh no, Christmas is coming, and then exams coming, and we don't have time for the last homework. Do you have time for the last homework?
No.
The deadline will be by tomorrow. No, I'm kidding, for tomorrow, but the deadline will be by Tuesday. But what happens is this. What happens is this. Did you do the second homework by yourself?
Yeah.
Okay, cool. Because it's the second homework. It's PCA. The same database. Same code. You don't need to touch anything. But you know that if you were using MATLAB, you had a comment, RGB to gray. don't use that comment. So you have an image which has already 3 channels. So we can have it in RGB channels. So you have 3 decisions in your hand. So if you run your code, you will get 3 results at the end. You will get the 3 results at the end. And so you have sets of decisions, and you can apply any of these techniques in order to see what is the final decisions. You will see that the result will be better. I know that your answer is no. I don't know why. I'm not surprised when you said you don't want to do it. But I know a better technique that at least 90% of you will do it. And the technique is this. I can introduce to you this homework as a bonus to your total grade. And Eric, surprisingly, you will see that most of you will do it. But if you don't do it, it will not have any negative impact on you. Most of you already know what you have done. You already have a good feeling that how you have to do. But because I don't want you to make a decision after your final exam, so the deadline for this one will be by 28th of December, because on the 29th we have the first. Because if you come to the exam, we can understand whether you do need the bonus or not.
How much bonus?
Huh?
How much are we talking?
Oh, now we are bargaining, right? What was the, I don't remember, if you do remember, what, you can stop the video.